Good evening, gentlemen.
Hey there, good
Hi there.
evening.
Hey, can
Here
you
we
hear me,
are.
John? Ah, there
Oh,
you are.
Here
we
we
can
are.
hear
Yep.
you. Yes, we can. We're up
Oh,
here at the Chabot Space and Science Center movie set.
yes, that's right. And movie
Yeah,
set. They are
yeah.
filming a infomercial in the dome next door to ours, so we won't be yelling quite as loudly. We don't want to upset them. So there's a little bit of
They
background.
already came and slammed the door on us.
That's right. Listen,
Unfortunately, the roof is still open, so the
Yeah, yeah,
sound
yes.
just goes right over.
that's right. It wasn't a very effective sound mitigation effort. Um, anyhow, welcome to another chapter of Saturday Night Virtual Telescope Viewing, and I'm Rich Ozer, and I'm here with Gerald McKeegan and John Curry, and thank you all for joining us. I want to thank Fremont Bank for their generous sponsorship of this program and other Chabot programs, and I want to thank everybody who has become a member over the last several months. And if you're so inclined, you can help us out with a donation on the Facebook page. There should be a button somewhere on your screen, depending on which operating system you're running. And if you're not on Facebook and you're watching on YouTube, or you're on the movie crew listening to what I'm saying and they're not watching at all, you can visit the ChabotSpace.org website and make a donation there or learn how to become a member. We are still closed until November, and we depend on the community to keep us going, and we appreciate anything you can do to help out.
And we
So,
do thank you all the
yeah.
ones that have donated, and those who are about to donate. Thank you very much. We appreciate it.
So
What,
that's
what,
my infomercial for the night.
yeah, one thing I
Yeah.
wanted
Yeah.
to point out, although we are closed to the public, we are not doing the typical weekend free public viewing that we've used to do before the pandemic. We are going to have a couple of public nights. They're ticketed events. So if you go to the Chabot Space and Science Center web page, chabotspace.org, and look in the events section, you should find where you can sign up for that. It is a ticketed event unless you are a Chabot member. And as Richard said a few minutes ago, if you go to the Chabot website and sign up as a member, then you get to get in for free. But if you're not a member, it is a ticketed event. We are going to open all three of our telescopes up to a crowd of up to 200 people for a viewing night. So you can actually come up and look through our telescopes rather than staring at your computer screen. So something to look forward to. We're going to do that on July 24th. Then we're also going to do it again in August and again in September. So something that you might want to think about.
Excellent.
Yeah.
Great. So, couple of announcements that are worth making, aside from what we've already talked about. The big news today is that the excellent team at JPL have fixed the Hubble telescope. And the problem, as some of you remember, is that the main payload computer on the Hubble Space Telescope was no longer able to read its RAM. It's just like going and buying a PC and having it intermittently glitch out on you, and then you turn it off and turn it back on and it keeps doing the same thing, and then you go out and you buy a bunch of RAM thinking that's going to fix it, and it doesn't. And basically all of those same things were happening on the Hubble Space Telescope. It was very, very familiar story.
Were
And
they
so
going out and buying a bunch of
Yeah,
extra
yes,
RAM?
they
I was.
did. They bought a bunch
I
of
was going
RAM,
to
and
ask.
they sent this guy out and
Yeah, right,
replace
right,
it
right, right,
from
right.
from the Geek Squad. No, but
Just go up there and put this in the computer. No problem.
in all seriousness, they did try the backup payload computer. That did not fix the problem. It was experiencing the same problem, which was a big clue that the actual problem was upstream from that. And so the upstream systems have backup power supplies, and they really felt that the problem was with the power supply because they weren't getting the right voltage readings off of the instruments in the payload. So they switched to a backup main computer, which also had a backup power supply distribution system, and they then booted the backup payload computer, and everything seems to work. And they're talking, and that's pretty amazing. They really pulled a rabbit out of a hat. There's a lot of redundancy on the Hubble Space Telescope. They did an excellent job planning for all of these types of contingencies, and it's really paid off over the years because this is not the first time they've had a crisis wondering whether or not the spacecraft was going to survive that particular fault. So we got a little more time for the Hubble.
Yeah. A little more time until the James Webb Space Telescope gets launched. And
Yep.
Richard, I understand that you got to see the James Webb Space Telescope.
Yeah, I did. I got to thank Alan Roche for organizing a trip for himself and myself and a friend of ours from Southern California. And it was one of our former galaxy explorers here at Chabot who, after he finished college in engineering, went on to work for SpaceX and then went on to work for Northrop Grumman, and invited us to come see the James Webb Space Telescope. And if I may, I will share an image here. I wasn't able to take my own photographs because photographs were forbidden, and we had to rely on NASA photographs, but I will give you an idea of what it is we saw. Hold on here.
So there are no photographs of you putting your initials on the side of the
No, or touching it, right? Right. So, or leaving my fingerprints on the mirror.
Scratching
Right.
it in there.
So what you see here is a partially folded up, pardon me, James Webb Space Telescope, and this is more or less what it looked like when we were in the observation room up above the assembly floor. And what you're looking at there, those gold colored pieces, are in fact most of the segments of the 18 segment mirror that is going to be folded up and then later unfurled when it reaches its proper orbit. You could see that 3 of the mirror segments are folded already off to the left, and there are 3 just like it off to the right, and the remaining ones will remain in that configuration. And the reason they're gold colored is because the coating is actually gold. So the mirrors are made out of beryllium, and the reason they're made out of beryllium is that is the lightest metal that can be machined accurately and strong enough to survive a space flight. And the reason it's coated with gold is because this telescope, unlike the Hubble, is going to be looking and in the infrared spectrum. The reason we're interested in looking in the infrared spectrum is that allows us to see further into the past. It allows us to see galaxies as they were forming very close to the beginning of known time. And there's a reason that infrared is more representative of that. And the best example I can think of for explaining the nature of infrared light is if you're standing next to a train track and not on the track, that's not very safe, but if you're standing next to the train track and the whistle is going, as the train approaches you, you hear the whistle increasing in pitch, and as the train passes you, it decreases in pitch. And you've all seen that on movies, and you've probably experienced it yourself. It goes, ooh, and that decrease in pitch is analogous to what light does when it is receding, when the object that emitted that light is receding from us. So a galaxy or a star that's moving far away from, that's moving fast, and let me say this again. A galaxy or star that's moving away from us very quickly due to the expansion of the universe is going to be sending light out, but that light is going to be stretched, just like the sound waves were stretched when you were standing next to the train track. And that stretch is infrared. When it's compressed, it's violet. When it's stretched, it's red. So we want to look at objects that are receding from us as quickly as the known universe allows. And those objects are very heavily shifted into the red, and in this case, the infrared. So the Hubble Space Telescope was able to show us everything in the visual spectrum, closer objects in great detail, but had a maximum observation that did not allow us to see objects that were really, really close to the beginning of time. And the Webb telescope will hopefully give us additional information about the origins of the universe and give us detailed observations of the oldest known galaxies. It will also allow us to see through dust clouds, because infrared light will penetrate dust clouds, whereas visible light, light visible to our to the naked eye, is blocked by those dust clouds. So there will also be a lot of study of the Milky Way galaxy and the dust lanes surrounding other galaxies, and hopefully we'll get additional detail about what's behind those. So anyhow, ask questions. I know that wasn't necessarily the best explanation in the world about infrared light, but it's hard to explain. So correct me or elaborate if you'd like. Anyhow, that's the news about the Webb telescope. It's going to be launched October 31st. Or possibly a couple weeks after that from French Guiana, which is in South America, the east coast of South America in the Amazon. The European Space Agency has a spaceport there and will be launched on an Ariane 9 rocket. And knock on wood, it's a new design for that rocket, and hopefully it will perform flawlessly, because this is a $10 billion instrument and there isn't a spare, although apparently they have a lot of spare parts that will never be used.
I got a question for you, Richard.
Sure.
Did you have to wear a bunny suit, or were you in an observation area outside of the clean room?
We were in an observation area outside of the clean room. Everybody who was on the floor of the clean room was in a double layered bunny suit and with all kinds of masks. And they keep the teams together, apparently. There's 2 shifts that work on the telescope, morning and evening, or morning and afternoon, evening, and they always keep those teams together. They don't really have people coming in and out while they're working. That way everybody gets to know one another and they learn how to work together efficiently, and also they don't want a lot of people entering and exiting during a shift in order to minimize the amount of dust. It's one of the cleanest assembly buildings in the world where they've got this telescope right now, and it's been there for 10 years. Who knew? Who knew? It's been in Redondo Beach for 10 years.
At one space park, Redondo Beach.
One space park where you used to work.
Yeah, well, I didn't work there. I was there a few times working for somebody else, but I was in their facility several times. Yeah.
Well, didn't you work for Northrop Grumman, or
no? I did not.
I thought
for
you
a company that was a subcontractor to Northrop Grumman.
Got it. Okay,
and
cool.
Boeing and McDonnell Douglas and on and on and on. You know, so.
Yeah, Renato just pointed out that the phenomenon that I was describing is called the Doppler effect, and that is very true for sound. The shift in light is not quite the same, because it's very similar.
We still call it the Doppler effect. Yeah,
we do call it the Doppler effect, but it's caused by something different. It's caused by the universe expanding and making things relatively recede from us. it's not like someone's gunning the engine and that one object is moving away, although it would have a similar effect if it did that. But the entire universe is expanding, and those farthest objects are receding from us most quickly because they're on the other side of the loaf of raisin bread that describe if the universe is a loaf of raisin bread and you're on one side, the other side is receding as most quickly away from you, with each raisin being a galaxy. So think about the rising bread and then all of those raisins expanding away from one another, and that's what we're trying to see is the furthest raisin.
Yep. The raisins that are closest to you expand away from you the slowest.
Right.
The ones that are farthest from you expand away the fastest.
That's a lot of raisins.
That's a lot of raisins.
And I bet you there are a lot of people out there right now trying to scratch their head and figure that out.
What are they talking about?
They think we've gone completely bonkers.
There's a neat demonstration you can do with an elastic band that kind of demonstrates the same idea, but we'll have to wait till you see us in person to do that. So, hey, you know what? I think we're looking at the moon.
Yeah, let's look at the moon. Actually, it's drifted out of view. I'm going to share my screen. You're going to need to nudge the scope a little bit. You've got it set to sidereal.
Wrong tracking.
No, I don't.
No?
You don't? That's interesting.
Okay.
Well, let me go ahead and
Well,
share my screen here.
while you're doing that, let me ask a question to our chat folks. Last week we talked about trying to view Venus in the daytime. I'd like to ask and find out if anybody tried that and whether or not they were successful. So just go ahead and chat about that if you like. Meanwhile, there's the moon.
There it is.
Coming back.
There it is.
Oh, and it's finally settled down a little bit.
Yeah,
it was really good. The seeing was a little bit jumpy earlier, and now it's pretty steady.
Yeah, so we're looking at the moon right now. It's I think it's a little bit past first quarter, and so we're looking at the west of what to us looks like the western side of the moon, but if you're on the moon, it's actually the eastern side of the moon. There was a lot of debate about that back about 30 or 40 years ago about which way we were going to call it. We decided that what appears to us to our west on the moon is the east. So we're looking at the eastern half of the moon, actually the north part of the eastern half of the moon. You see one crater near the terminator. The terminator is the boundary between the dark and the light area. And you see a crater there that looks very smooth in the middle. And that has a nice high rim around it. That's the crater Plato. Plato is at the northern end of the Imbrium Basin. The Imbrium Basin is a very, very large impact basin. It's about 700 kilometers in diameter, and it has filled with lava. That impact was so forceful that it cracked the crust of the moon. And this was back about 4 billion years ago when the moon still had a molten interior. And so lava oozed up through those cracks, filled the crater left behind by this big impact. And it now looks like a very smooth plain with a few craters in it, newer craters in it. And Plato happened to be a crater right at the upper edge of that big basin. And so it filled with lava as well. So that's Plato. Looking to the right of Plato and a little bit, almost straight to the right, you can see a very, almost like a straight line. Richard, you're going to have to point this stuff out here because.
Yeah, I know there's some way to do.
Yeah, right there. There you go. Yeah,
so I got it right there.
That's called a graben. Its official name is the Alpine Valley, and that mountain range all around it is called the Alps. They name mountain ranges on the moon after mountain ranges on the Earth. That Alpine Valley is caused by a crack in the surface of, or the crust of the moon from the Imbrium impact, and that crack filled with lava, just like the main basin did. And so it's this nice, smooth, straight line extending away from the center of the Imbrium Basin. The official term for that kind of feature is called a graben. A little bit farther to the east of there, you see a couple of craters, kind of up and to the right of the Alpine Valley. The upper one is called Eratosthenes, and the lower one is called Eudoxus. Richard, I can't point out, so you're gonna have to do it.
Sorry, there we go.
That's Eratosthenes, and then the one below it, that's Eudoxus. Then coming down, you see below that another mountain range that's right on the rim of the Imbrium Basin. It's called the Caucasus, named again after a mountain range on Earth. The crater right at the bottom of the frame, that crater is called Aristillus, and then the one that's only half in the frame just below it, that's called Autolycus. In fact, I think I'm going to move the image here a little bit. Maybe. There we go. So that's Autolycus that he's pointing at now. Then the one to the left that's got another smooth floor crater, that's Archimedes.
That's a really remarkable looking crater.
Yeah. And again, this is a crater that occurred after the original Imbrium Basin was created. And when the Imbrium Basin filled with lava, that process actually took hundreds of thousands of years. And so, in fact, I think it took over 1 million years. And so over time, that crater that's Archimedes, it filled with lava as well.
I would like to point out, this is actually a perfect example of why we like to look at the moon when it's like a quarter moon or partial moon.
Yeah.
So the sun is coming in from the right-hand side of the screen as sunlight. And you can see that here's the crater wall. And whoops, I'm drawing.
You're cheating.
I'm cheating. And down below it, you can see the shadow, right?
Yeah.
So if you were standing there in the shadow of that crater wall, it would be very cold and very dark. But on the other side of the crater, you could see the sunlight hitting the edge of the crater wall here. And it's the other side that's in shadow. So you could kind of, deduce that the sun is coming in this direction. And if it wasn't for these shadows, it would look rather gray and bland. We wouldn't be seeing this sense of relief that we can only see during a partial moon, during a phase of the moon.
Okay, can you get rid of that line that you're
I
doing
am
now?
trying desperately.
While you're doing that,
Undo.
Yeah,
if you look to the
I
right-
cannot figure out how to get rid of the line.
Okay.
I'll have to.
Night.
Yeah, it is going to be a long night. Sorry about that.
Reload the picture.
Yeah,
Oh, that's a live view, isn't it?
Yeah, it is. So I'm not quite sure. Let me stop sharing and share again.
In the meantime, Lisa asks, she's seeing a lot about the moon's wobble in the news. I didn't know.
Oh, yeah.
Much in the news.
Yeah. There's been a story. A paper came out here. Actually, it came out in June about how one of the many wobbles of the moon caused or is causing global climate change and global temperature increase, global warming, to actually ramp up even faster than it would otherwise. And the wobble that they're talking about is not the wobble that most people think of. There's a wobble that the moon does called libration, and it's the poles of the moon tip a little bit one way and then back the other way,
Right.
and then the moon also tips side to side a little bit each way as it orbits around the sun. That is not the wobble that we're talking about. This wobble has to do with an 18.6 year cycle that the moon goes through, during which its angle above the equator changes during different times, and sometimes its gravitational pull on the tides actually is stronger than it is at other times. And there's this, like I say, there's this 18-year cycle, and as a result, there are certain times when it pulls harder on the tides of the Earth, and we're actually moving into that period where, because of the way the angle that the moon will be above the equator, it's going to tug a little harder on the tides. And as a result, the tides, especially starting after 2025, the tides are going to be higher than typical. And if you superimpose that over the increase in sea level caused by global warming, it actually amplifies how high the sea level will get going forward in time. It's a complicated idea, and when you read the news articles, which don't go into the technical details, they just say the wobble of the moon is going to make the tides higher, and it's going to make sea level rise even worse than it would be otherwise. So,
Gerald, is it correct to say that the reason this happens is because the angle of the moon with respect to the equator places it over a greater volume of water?
Yeah, but the other thing, the moon's orbit is not parallel to the equator. The moon's orbit is actually tipped about 5 degrees to the ecliptic, which is the plane of the Earth's orbit around the sun. And it varies. I think it goes between 18 degrees above the equator, and it can be as high as 25.5 degrees above the equator, or north of the equator, or south of the equator. So sometimes it's much closer, it stays much closer to the equator, and at other times it swings much more widely. And it does this over an 18.6 year cycle. And it's going to, in 2025, it's going to be at the point where it's at the maximum. And therefore, it's going to pull a little harder on the ocean, especially the northern hemisphere ocean, and
Right.
that's going to increase the tides, makes the tides higher. And when you combine that with sea level rise, it's going to mean we're going to get even more inundated shorelines than we would otherwise if it was just because of sea level rise from global warming. So
yeah, I mean, the places to be concerned are places like Venice, which are already, right on the line of being inundated on a monthly basis. And
I apologize for not explaining this very well, because it really is a complicated concept. It's better explained with diagrams and things like that.
Join the club.
So just understand that the wobble they're talking about is not the wobble that most people think of, which is that libration. It's a different kind of wobble. It has that 18.6 year cycle. So anyway, back to the moon.
Yeah, thanks for
now that we got rid of the line.
Thanks for the question, Lisa. That was a good question.
Yeah, it was.
So we were talking about that's round, smooth crater Archimedes down there near the bottom. I want to shift it a little bit here. Maybe. Oh, all of a sudden we shifted a lot. Well, that's okay. So to the right of Archimedes, you see a long arcing mountain range. And this is yet another mountain range named after a mountain range on Earth. This is the Apennines. And right about in the middle of the arc that you see there is a place, we can't see it in this image, not very well anyway. It's called Hadley Rill. And it's right at the base of the Apennine Mountains on the Imbrium side. And that is where, no, it's actually a little bit higher and much closer into the mountains.
Okay.
And that is where Apollo 15 landed. So just kind of, curious little detail there. I'm going to go a little farther south here. All right. So the crater that you see just inside the lit part, that one right there, that's Eratosthenes. And Eratosthenes, you've noticed we're getting a lot of Greek names, Greek philosophers and things. Eratosthenes was a Greek philosopher. And about, I want to say around 250 BC or BCE, depending on how you want to call it. He was the first to make a reasonably good effort at measuring the circumference of the Earth. So contrary to popular belief, long ago they knew that the Earth was round. And Eratosthenes came up with a way of measuring the circumference of the Earth. He was at Alexandria at the northern part of Egypt. And farther south, about 500 miles south in Egypt, is a place called Syene. I don't think it's called Syene anymore. Back then it was called Syene. And in Syene, right in the middle of town, was a well. And in certain days of the year, the sun would be straight overhead of the well at noontime so that it shone straight down the well. And there were no shadows inside the well. And Eratosthenes had heard about this. And so he decided to do an experiment. And he set up a pole and he got it as vertical as he could in Alexandria. And he knew the distance between Syene and Alexandria. And so he waited until that day when the sun was going to be straight over that well. And he figured that whatever difference there is between the shadow of the pole in Alexandria and the point in Syene where there is no shadow, that angle represents a portion or a fraction of the circumference of the Earth. And so using that and knowing the distance between the 2 points, he was able to compute the circumference of the Earth. Now, his number was off a little bit, but not a lot. It was a pretty good number given, the crude method that he was using. And scientifically, that method is perfectly legitimate. It is a perfectly valid way of doing it. Of course, today we would do it with a lot more precision, but his technique was sound, and he did come up with a number that was a pretty good number. So that's the crater that got named after him for figuring out how to measure the circumference of the Earth.
And it looks like a pretty deep crater.
It is. It's a relatively young crater.
Yeah.
So, Richard, point out the terminator there because there's been a couple of questions answered already in the chat, but just want to show.
I'll try not to use the annotation tool to draw a picture of Arnold Schwarzenegger. The terminator is right here. It's this.
Ouch.
It's this line between light and shadow.
Speaking of light and shadow,
we just got illuminated by like a Klieg light outside.
Yeah, we're having a little fun here with this movie crew here. So what I wanted to do is kind of move off to the right a little bit here. There's a big smooth area. Right there, that's called Mare Vaporum, the Sea of Vapors. And going even farther to the right.
Aha, that looks familiar.
The Sea of Tranquility, right there. Yep. That's the Sea of Tranquility. Up above it is the Sea of Serenity. Right there. So
yeah, that's a good area to point out the effect of the sun being a much shallower angle.
No shadows. You can't tell how deep the craters are or how high the mountains are or anything like that. Yeah,
perfect illustration of what I was talking about here.
Yep.
Yeah. So we're going to get down here, and we're going to get down to this feature right here. If I can get it centered up here. We call this the Snowman, right there.
Yeah.
So it looks like an upside down. In this image, it
Yeah.
looks like an upside down snowman.
Yeah.
Depending on the type of telescope you use and the
There's the
configuration of the
nose.
eyepiece,
There's
sometimes the moon appears upside
No.
down, and you're told you gotta.
Sometimes it's got a smiley face.
Sorry, I couldn't resist.
Anyway, if you use a certain kind of telescope with a certain eyepiece configuration, this whole image would be upside down looking through the telescope. So the small circle, the one where Richard has crudely and rudely drawn facial features, that would be the head, and then the body, and so on and so forth. So we call this the snowman. All right. Now
All
you
right.
gotta get.
I got
get
it.
rid of it?
Give me a sec. Give me a second. There we go. All right. There we go.
Got the Three Stooges up here.
Pretty much. It's been that kind of day for me.
So I just want to kind of finish up the moon here by coming on down here to this part of the moon. We call this the Southern Highlands. We were showing you regions where there were a lot of what we call seas or mares, or actually the plural is Maria, not Maria, Maria. This is called the Southern Highlands. This is actually an older part of the lunar crust. It's more heavily cratered. There are no big basins, so there's nothing that's, or not very much, that has been filled in with lava. And it's much more jumbled area. The cool thing is, if you go all the way down to the bottom here, you notice how the shadows get longer and longer as you get closer to the south pole of the moon. Well, it turns out that if you go far enough south, you find craters that the bottom of the crater never gets lit by the sun. It's so far south, and the moon happens to be oriented so it's north and south pole are almost straight up and down relative to the light coming from the sun. So these craters, the bottom of these craters never get any sunlight. The moon is overall extremely dry. If you go somewhere in the middle of, say the Sea of Tranquility and pick up some dirt, what we call regolith on the ground, and try to analyze it for water, you don't find much. There's just not a lot of moisture in the ground. But we have determined that in these craters that are constantly in shadow, there is moisture. There's actually water ice in there. And what happens is, all these craters are produced by asteroids and comets hitting the moon over the last 4+ billion years. And the ones that produce craters at the poles, if it's a comet that produced that crater, or if it's an asteroid that has a lot of ice in it, some of that water will get left behind, frozen inside those craters. And it turns out there's a huge amount of water in these craters at the South Pole and at the North Pole. So that if we ever send humans back to the moon and actually build a colony on the moon, we're likely to build it close to one of these poles, because that's where we're going to get the water. And if we don't have to transport the water from the Earth, that saves us a lot of weight and makes it a lot easier to sustain a colony on the moon.
And what we would have to invent is water mining equipment that could survive extremely low temperatures.
Yeah,
because
really.
in those dark parts of those craters, it's very, very cold.
Yeah, minus 300 degrees Fahrenheit.
That's right.
Yeah, very cold. And at that temperature, ice is as hard as a rock. I mean, literally as hard as a rock. So, they're going to have to overcome that part. But I'm sure if there's a will, there's a way.
Yep.
Okay. Well, we got a nice tour of the moon there.
Yeah, we got some questions.
Good question
Right.
came up. Who gets to name the places on the moon and all of that? It's actually the IAU, the International Astronomical Union, gets to name pretty much everything in the sky.
Yeah,
including craters on the moon. And
that's how it is today.
Right.
In the past, there were various individuals back in the 18th and 19th centuries who would name the craters on the moon. And they sometimes different people would give different names to the same crater. So eventually in the 1930s, the International Astronomical Union, they got together and said, okay, we gotta, stop having different people give different names to the same object. So they established a committee that's responsible for naming all the craters on the moon and, the asteroids and
all the stars, all the constellations,
all that other stuff. Yep. And speaking of stars, you cannot buy a star and get it named after you. You can pay somebody to give you a certificate that says it's named after you.
Completely phony.
The International Astronomical Union will just look at you and say, sorry. So be forewarned.
That's right.
All right. Well, should we leave the moon and go somewhere else?
I think it's time. I think it's time to leave the moon.
Yeah, we've actually been doing this for quite a while here already.
Yeah.
So.
Oh, it was a pretty good tour.
Yeah. So what do we want to do? We want to do the carbon star?
I think that's a good idea, and we got to take some shots of it as well.
Please,
so,
please. I'm going to need some photographs of that. So.
All right. Well, we'll try to do that.
All right. Let's see. We're not that far away from it, but let me just kind of get over there.
All right, what we're going to be doing is looking at what's called a carbon star. And a carbon star, its most notable characteristic is that it's very red. And
stay in live view.
I will right now, because you're gonna be aiming this thing, right?
Right.
All right, let me put the grid up. So as stars progress through their lifetime, they burn up their hydrogen, they burn up their helium, and this is all done through nuclear fusion, and eventually it reaches a point where it's got a very large percentage of carbon, and carbon, as you can imagine, glows like a red ember, right? It gets hot and glows a very deep red, and it's towards the latter part of a star's life that it might become a carbon star. And there's many excellent examples of carbon stars in the visible sky that are viewable through small telescopes, and certainly viewable through Nellie. And we're going to take a look at one that's in the constellation Aquila, right?
So, Richard, the reddish color isn't actually coming from glowing carbon, though, isn't it? It's more that it's blocking other light.
It is cooler than most other stars, and and that drop in temperature also contributes to its red color.
But it's also blocking a lot of the other wavelengths of color, so that's why the red shows up. Okay, where are we there? We're looking at
Altair.
Altair, okay.
Oh, there we are. Yeah, you're dead center. That's good. Right. Close enough anyway.
Yeah, okay. How are we doing on focus here?
It's not bad. I don't think it's going to get much better than that.
Yeah, there is a bit of a breeze tonight, especially up high in the atmosphere. So we're
that's about as good as you're going to get right there. As good as
we're going to get right there.
Right there.
Yep.
Yeah. Yeah, you're not going to get now. Now it's. Oh, you just moved it. That's what happened.
Sorry about that.
That's okay. I thought all of a sudden it was.
Okay,
going off the rails.
We're on Altair, and we are going to go to.
You did sync it first, right?
Yeah, I just did.
Okay.
I'll do it again, just for you.
All right.
Sink or swim.
Sink or swim. There we go.
Okay, here we go. Altair is on one end of Aquila, and this carbon star is on the other end of Aquila. And I'm not sure, it's magnitude 6.5, so I'm not sure.
I don't think we're going to be able to see it in live view.
Yeah,
but I will try anyway. Yeah, actually, maybe that is it right here.
Oh. Gee, you can see that better than I can.
Hold on. Let me
I didn't see anything there.
let me drop the exposure.
Yeah.
Are you
I
sure
see
that's
it.
not a? I see a red thing there. Is that a?
Yeah, no,
not a hot pixel or
that's a
anything?
hot pixel. This
Okay.
is the star.
Yeah,
and
that's
it's
it. That's it.
very, very red.
That's it.
Yep.
It's it.
Yeah.
Oh, I like
Right.
this one.
That's
yeah.
a good one. Yeah, it's a nice
Yeah.
deep red.
Look at how red that is up there in the zoomed view on the upper right there.
Yep. So let me switch over to imaging view. This is taking, this is eighth of a second. All right, let's try. Pardon the moon here for a sec. Let's go to.
Excuse my moon.
Second.
You gotta do just like 1 or 2
Yeah.
seconds.
Yeah.
Don't go too high on the ISO though, because
Yeah, I don't want a lot of noise.
Yeah, yeah.
Let's actually let's see about doing it at 1600 for a second here, and we'll adjust.
How long of exposure are you gonna do?
This is just 1 second, and I'm going to work my way up.
So there should be a lot of stars around this guy.
There we go.
Oh, there you are. Yeah.
All right. Does that suit your needs to do several of those, or?
I kind of like to get a shot so we can see some of the other stars around it. There should be a lot of them. So maybe go like up to 10 seconds or something like that. Probably saturate it, right?
Yeah, that's what I'm worried about. Well, let's see what happens.
The reason we're doing this extra work is because in a couple of weeks we're going to be shooting another movie up here. And they want to actually get an image of this.
Huh.
Yeah, there we
go.
Oh, beautiful, beautiful.
Okay, let me take several of those while we're talking.
Please.
So I'm going to take.
Yeah. So you see the orange color of this. As we do longer exposures, it gets brighter. But as Richard was saying, the carbon in the upper part of the atmosphere of the star absorbs blue light, and because of that, it's only the reddish part of the spectrum that gets through. And so this is what we see is this. We call them carbon stars. And when you look with your eye is actually more sensitive to red. You can get some really good views of a deep red star.
So the thing to do is compare.
Oh, because I'm tracking at the wrong rate. That's dummy. Still at the lunar rate. Yeah.
The thing to do here is take a look, if you have this on a computer screen or if you expand your cell phone screen, compare this star to all the other stars in the field, and you get a really good sense of how different these carbon stars are from younger, more standard stars.
You see a lot of blue stars in the field. Those are young stars. They're massive stars, but they are still early in their life, so they're main sequence stars. This orange star that you see here, that's a star that's approaching the end of its life, and it has swelled up and it's become cooler in color because of the carbon that's being churned up from down deep inside, where it's fusing helium into carbon.
Bob is suggesting you take a slightly shorter exposure to bring out more of the red.
Yeah, let's get a couple of these shots and then we can do a shorter exposure.
Also, Renato,
maybe a 5 or 6 second exposure.
Also, Renato says not all red stars are carbon stars, right?
That's true.
That's correct.
That's true. A star that has very low mass will be reddish in color because it's not very hot. How many you got there, Richard?
I've got it. I probably have enough. Let me let me go for the shorter one.
Yeah, maybe a 5 second exposure.
Yeah. Let this finish downloading.
So there actually are a lot of these stars out there. You can get handbooks that will tell you where all of the carbon stars are, and they're all over the sky. And they're just really neat to look at because of that deep red color that you see. And because the star has swelled up, it's a relatively big star, which means it has a lot of surface area to radiate light.
Yeah, I think this will do the trick.
Yeah. So who was it? Bob wanted us to use a shorter exposure?
Yeah, this
So
is.
Bob has to tell us whether this is good enough or whether he wants it even more red. 2-second exposure.
Well, I can always.
Well, when we first saw it, though, it would look pretty cool.
Yeah.
Did we lose our YouTube feed or something?
Oh,
I'm getting this
watching
slide
YouTube
on there
right now, and I see it.
Oh,
hit
Yeah,
the
refresh your screen.
Refresh.
Yeah, I'll do that. Oh yeah, better.
Yeah, Bob wants 1 second.
But then we can't see the other stars. We aims to please, Bob.
Yeah, there we go. We'll give you a 1 second, Bob, but no more.
Or you mean no less?
There you go.
Yeah, that's pretty
All
red.
right,
There you go.
There you go. Except now we can't see the other stars.
Right.
That's right. So now I have to do an HDR combination. All right,
So
I think that's good.
I'm not sure, guys. On mine, it looks like we've lost on Facebook. Oh, there it is. Never mind.
Yeah, you guys keep thinking it's all gone. I'm sitting here monitoring both of them, and they're fine.
Well, yeah. On the receiving end, glitches happen. That's all.
Yeah.
Okay.
Now Bob wants you to stack the images. This is it's getting too involved here.
He wants me to do. He wants me to do processing.
We only have an hour, Bob.
so,
so where else were we gonna go? Were we gonna go look at the Ring Nebula?
Yeah, we should.
Or
We
did
should
you
take
have
a.
something else in mind?
No, I think the ring is a good idea because
All
the
right.
moon is pretty bright, so we don't want to go looking for anything too difficult
Yeah,
tonight.
yeah.
So let's
Not that
go.
bright.
The bright light from the film crew is pretty bright too.
Yeah,
It's,
that's right. We have the
affecting
film crew,
things.
the film crew Nebula outside here.
All right, so I'm gonna go ahead and slew to the ring then.
Okay, you going straight there? Or are you gonna?
I'm gonna go to Vega first, and
Okay,
we'll sync on Vega, and then head over to.
That should be pretty close. Yeah.
Yeah.
So I think looking at a planetary nebula is a good sequel to looking at a carbon star, right?
Yeah.
I mean,
Right. It's the next
step.
thing down the road.
Yeah. All right, there's Vega.
Yep. And let me see if I can get it centered up here.
Boy, that looks like a basketball.
Well, I can.
From this, it's from the seeing. It's not from the focus.
But it looks pretty round. So
Yeah, it's pretty
that's a good
round.
thing.
I think we're okay.
All right. All right, and then off to the ring. And that one you're going to have to shoot like 30-second images.
Yeah.
So we're going to the Ring Nebula. The Ring Nebula is what we call a planetary nebula. A planetary nebula is the remnant of a dying star. So the Ring Nebula was a star that was once very similar to our sun, but it is a much older star than our sun. And as stars age, they swell up, eventually become red giant stars. And there's a lot of churning going on inside the star as it switches from fusing hydrogen to helium and starts fusing helium into carbon and so on and so forth. As the star gets very big, its gravitational hold on its outer layers becomes much weaker.
Oh, we caught a satellite.
Hey, look at that. Was that a satellite, or was that plane that just went by?
It could have been the plane, but I don't know. It doesn't seem like that was. Yeah,
I think the plane would have been much brighter.
I think so too.
Yeah,
Yeah.
probably. So
That's not
so
bad,
anyway, the red giant star starts blowing all its outer layers out into space, and this goes on for tens of thousands of years, or even hundreds of thousands of years. Eventually, the star loses more than half of its mass just from all this gas blowing out into space, and as that happens, it exposes the interior of the star, which is much hotter. And eventually, the fusion process at the core of the star stops. And when the fusion stops, you no longer have the outward pressure caused by that fusion process. And so the star collapses, becomes what's called a white dwarf. White dwarf is very small, it's extremely dense, and it's extremely hot. And it's so hot that it emits a lot of its energy as ultraviolet radiation. The white dwarf is surrounded by all that gas that was being blown off while it was still a red giant star. And the ultraviolet radiation ionizes the gas or excites the gas, as the case may be, and causes it to glow. And so that colorful ring that you see is actually the glowing gas that surrounds the white dwarf. The white dwarf is right at the center of the donut hole. I don't know if you want to try to zoom in and maybe we can see the white dwarf.
Let's see if we can do that here. Yeah, so you can see it right here. I'll move my cursor and let's see if I can.
Don't draw on it.
Let me draw a face on it.
That's kind of cheating.
Yeah, I won't draw it this time.
Yeah, so
that's
the white dwarf. The ring part, the part that you see, is about a light year across, maybe just a little bit less than a light year across. But what you see is only part of what's actually there. You notice that the outer fringe is kind of red in color. That tells us that this has a lot of hydrogen in this cloud. But hydrogen, it has to be excited to a pretty high energy level before it will glow red like that. And as it gets farther away from the white dwarf, it still gets excited, but not quite as much. And so it glows red, but it's such a deep red that we really can't see it, especially with this camera. But in fact, the hydrogen extends all out to the perimeter or to the edges of this field of view. The Ring Nebula is actually embedded within a very huge cloud of hydrogen gas that was blown off by the star while it was still a red giant. And if we were to put a special filter on the camera called an H-alpha filter and take a very long exposure, we're talking hours here, we would actually see that there's this huge cloud of hydrogen gas surrounding what we call the Ring Nebula. So the nebula that was produced by the gas being blown off the star actually extends much farther than what you see here. And this is very common. Our sun will go through the same process in about 5 or 6 billion years, and it will have its own planetary nebula. It might look like this, it might look different. Might look like an hourglass or a butterfly or something like that. But this is how most stars end their lives. Contrary to popular belief, most stars do not explode in a supernova. Fewer than 10% of all the stars explode in a supernova, and those are only the very massive stars. Most stars die in this very slow process that ends with a planetary nebula and a white dwarf at the center. Eventually, the nebula itself will drift away over the course of 1 million years or so. The white dwarf will continue to glow hot for several tens of billions of years, but it too will eventually cool and become what we call a black dwarf. It's not a black hole, it's a black dwarf. It's just the remnant or that white dwarf cooled enough to where it's no longer emitting light, and it is just a black ball of very dense matter out in space.
Renato points out that this looks a lot like the eye, I think he means the cat's eye nebula that we were looking at last week. And that's because it's a very similar object.
Cat's Eye Nebula is another planetary nebula.
Also, Michelle asks, are there any showy planets going into prime photo phase soon? Like Saturn?
Soon, yes.
Soon, next month.
Yeah, next month.
August, we'll start to see Saturn and Jupiter.
Saturn and Jupiter are just coming up above the eastern horizon right now. But in a month or so, it will be in range for our telescope, especially when we get the sun going down a little bit sooner. We're in fact in mid-August we're going to switch back to 9 o'clock instead of 9:30. So you folks who are staying up late with us, you won't have to stay up quite so late. But yes, we will be looking at Saturn for sure in August, and then Jupiter is a little bit behind it. And when it finally gets high enough and clears the other dome here, we will be looking at it as well. And that's going to be a lot of fun because there's a lot to see on Saturn and on Jupiter. So something to look forward to for later on the summer and into the fall. They're just having all kinds of fun with the lights on our dome over there.
I know, it's really distracting.
I know.
all this white light coming in through the front door here.
The interior of our largest dome here at Chabot, when we are observing, we have red lights on in there. But the movie crew has decided there is not enough red light in there, so they have gone in there and they have really lit up the inside of that dome with red light. It's quite beautiful, actually.
It is very red.
Yes.
But they've also got this bright white light on the outside here. So,
all right. Well, how are we doing on questions here? Anything that we need?
We pretty much kept up with most of what I see here. Let me look on YouTube, see if we've got anything more over there.
And Colleen notes that the Space and Science Center, Chabot Space and Science Center, still needs funds. Since we're not open, we're not getting the revenue that we would normally get from ticketing. So we do encourage you to donate. If you're on Facebook, there should be a donate button somewhere on the page. Otherwise, you can go to our website, chabotspace.org, and you'll see a donate button at the top of the page. Or you can go to the membership page and join and become a Chabot member. And I mentioned earlier the viewing opportunity that we're going to have coming up later on this month and also in August and September. For members, that is a free event. Everybody else, it is a ticketed event. If you're more interested in that, check out the events page on the Chabot website, chabotspace.org.
I think you have to sign up for it regardless of whether you're a member or not.
That's correct.
Right,
So
right.
they
Yeah,
limit the number.
I guess they have to limit the number.
Yeah.
I want to point out that Alan identified the satellite that was in
I see that.
Oh, yeah?
Yeah, he said
Great.
it was Global Star M002.
I knew that.
Global Star is a communications satellite.
Yeah.
And Colleen, thanks a lot for pointing out that comment about funding.
Yeah. Yes.
And also, no, we don't get to play zombie scientists. This movie crew is just here for an infomercial.
Yeah. It's an infomercial for a private corporate network. It's not even going to be publicly viewable.
Yeah, I tried to talk the director into making me, auditioning me, but he just kind of laughed, So.
Hey, Gerald.
Yes.
Laura is asking about green stars. She had asked this earlier, and we hadn't talked about it yet.
Oh yeah,
She asked the question: are there green stars?
there are stars that how do I say this?
Yeah,
They're
they don't appear
strongest.
green.
Yeah, they
Notice
don't
I'm
appear.
not trying to answer this.
Yeah, this is a really hard concept. So stars that are really red, if you plot the intensity of the light of the star across the whole visible light spectrum, it would be very bright in the red part of the spectrum, would be not so bright in the green part, and even less bright in the blue part of the spectrum. On the other hand, if we looked at a blue star, the slope of the angle would be the other way. It would be very bright on the blue side of the spectrum, not so bright on the green side, and even less bright on the red side of the spectrum. As it turns out, if the greatest intensity of light from the star is in the green part of the spectrum is almost level. So there's a lot of green, or it's most intense in the green part, but there's also a lot of red and a lot of blue.
Which
and
makes
as a
it
result,
look.
it's white.
Yeah.
so
That's right.
green stars are actually white. So that's kind of a hard thing to kind of explain without doing diagrams and everything. But the answer is, yeah, there are green stars, but they look white. So
that was a good answer.
yeah. So when we talk about
I
a star
totally get
being,
it now.
Yeah, when we talk about a star being blue or green or red, we're just talking about the wavelength, the color at which the light is most intense. But the light is there in the other wavelengths as well, to some extent or another. And when it's most intense in the green part of the spectrum, it tends to be almost as intense on either side of the green part of the spectrum. In the visible spectrum, the green is right in the middle.
So what color are the rarest stars?
The rarest stars?
According to Renato, I'm guessing like in the very, very blue range?
Well, yeah, it depends on what you mean by rare.
Yeah.
The blue stars, which are very hot, massive stars, those are actually the rarest type out there. But
because they don't last long
with our naked eye, the ones that you don't see, the most plentiful type of star out there are red dwarf stars, which are very red and also very faint. So we don't see them with our naked eye at all. And even in a telescope, they're often kind of hard to see. These are low mass stars. They're just hot enough to be fusing hydrogen at their core, but they're such low mass and the temperature of the core is so low that they're just not very bright, but they are very red in color. And those by far, there's more of those than any other type of star out there. It's just we can't see it because they're so dim.
Good answer.
All right.
All right. We have a question here about the Webb telescope, and is how distant will the Webb telescope be from Earth?
Almost a million miles.
Yeah. It's somewhere between a million and 1.2 million, I think, miles away. It's in a part of space called Lagrange 2, which is an area that is very stable with respect to the orbit around the sun, meaning that if you put something there, it's not going to drift. It's going to stay put for the most part, with just a little bit of adjustment once in a while. Whereas in any other part of space, gravitational tugs from nearby bodies would disrupt the orbit and fling it off into another direction. But Lagrange spots are very stable, so it's a good place to stick a telescope that has to, be in a predictable location, far from the Earth, but within radio communication range for many years. And it's going to be constantly pointed at into deep space, but the bottom of the telescope will be facing the sun. The top of the telescope will be facing away from the sun, where all the instrumentation is. At the bottom of the telescope will be facing the sun and will be blocking the transmission of that heat with a very complex and very high-tech solar shield that does nothing but dissipate heat before it reaches the other side of the telescope.
It's a parasol.
It's the size of 2 tennis courts. If you imagine 2 tennis courts laid end to end, that is how big this heat shield is. It's huge. And it's got 5 very, very thin layers of metallized plastic that are separated, I think, by about roughly 3 or 4 inches, something like that. And that is going to dissipate all the heat coming from the sunlight.
Michelle asked, isn't there some probe already at L2? The answer is yes. And they took that into account. They're going to be very careful in placing the Webb telescope's orbit so that there's not any risk of collision with another man-made object. That would be
that would be a bad goof.
That would be bad. That would be an embarrassment. But the answer is yes. And I forgot what the name of that other probe is. Gerald, do you happen to remember that?
There's one at L1.
There is one at L2, and it's something. I think it was designed to study. I think it was designed to study the cosmic microwave background radiation.
Okay,
but I'm not sure. Yeah. Anyway, maybe next week I'll have that for you.
Yeah, something to look up.
Yep.
Tune in next week.
Right.
Right.
Find the answer.
Yeah. So how are we doing on questions here?
What focal length are we viewing at right now?
We are
our stuff, not the web.
we are at 7,315 millimeters, or 7.3 meters, which translates to 24 feet for you metrically challenged folks.
And that's F8, right?
Yes, it's an F8. Yeah.
All right. Won't the heat shield act as a solar sail? Yes.
Yes, but
it will.
Not much of one. So
yeah,
it will act as a solar sail, but they have a way of compensating for it. So it's not going to go drifting off into deep space or anything like that.
Yeah, but it's a great question. I mean, on one side of the telescope is going to be hundreds of degrees Fahrenheit, and the other side of the telescope is going to be like 30 degrees Kelvin, which is hundreds of degrees below zero. That temperature difference is profound.
Yeah, you don't. Since you're looking at infrared, you don't want the telescope structure to be glowing in your field of view. So.
Tim just answered that Herschel and Planck were both at L2, but they kicked them out. They kicked them out they didn't pay their rent.
Kicked them out.
Yeah.
Once they're no longer useful, we throw them away.
James Webb Space Telescope is moving in, and you guys are out.
Yeah. There's a new boss in town. Great questions. Let's see. Anything else tonight? That's it.
All right. Well,
anything on YouTube? Just double check.
Nope.
Nope. I don't see anything.
All right.
It must have an RTG.
I do. RTG.
Yeah, radioisotope thermal generator.
Oh.
for electrical power.
Okay.
It's got solar panels on the hot side, so it's going to be powered by the sun.
All right. Well, I think we're done.
Yeah, last week I mentioned viewing Venus. I got a few responses that people had a hard time, but next month there's an actually easier time around August 10th and 11th. So we'll try it again next month. If you couldn't see Venus this month. We'll try it again next month. It'll be even a better position.
So, Richard,
Yes, sir.
would you go to? Oh, you did it. All right. So I'm going to point my camera at our dome, and you can see how it's all lit up and everything. Lots of red light on the inside and lots of white light on the outside. Good thing we're not doing any observing with that telescope.
Yeah, that's right.
All right. Well, thank you, everybody. Hope you enjoyed it.
All right.
And
We had fun.
We had fun, sure.
come back next week, same time, same channel, and we will hopefully have clear skies and something else to look at.
Yep.
All right. Have a good
night,
weekend,
everybody.
everyone. Take care.
Good night.
Just a sec.